Good morning, guys. Just recording a quick video on the rational zeros theorem. Um, First of all, I just wanted to record it because when I was screenshotting the notes yesterday, I realized in one class I had switched up the P and Q when I wrote the equation. So my apologies. So I wanted to just redo it for them, but also for the classes that don't meet today. So first of all, to clarify, again, in one of the classes yesterday, for some reason when I wrote the theorem down, I wrote the P here instead of the Q, like I switched those up. So just want to make sure that everyone's clear with that, first of all. So what the rational zero theorem is, it's telling us, it's going to give us a list of all of the possible rational zeros for a specific function. I'll show you how we use this in a little bit, but right now we're just going to practice using it. So what the theorem itself says, it says giving a polynomial in the form f of x equals q x to the n plus da 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 all the way down to p. So when it comes to this, the q is the leading coefficient. Q is the leading coefficient. And the p is the constant. So leading coefficient constant. So first of all, understanding what a rational is. A rational number is a number that can be written as a fraction. So when we're talking about our rational numbers, we're talking about numbers such as anything that can be written as a fraction. So we're talking about anything that can be written as a over b. So these are going to be whole numbers, things like a half, a third, etc. What are not going to be rational numbers? So it's not going to be any of our imaginaries, and it's not going to be anything that's a square root. So this isn't going to give us a list of any of those numbers. It'll just give us all the possible rationals. So the rationals are whole numbers, fractions, etc. So it says, so here for the theorem, it says the possible rational zeros of a function are all the combinations, plus or minus, of the factors of p over the factors of q. So this is basically what the rational zero theorem is. It's going to be a list of all factors of p, so not just p, but any factors of p over all factors of q. And then we're always going to plus minus them. So it'll be plus or minus for each one. So the first couple of examples here, excuse me, as soon as I start a video, I start to yawn. The first couple of examples here, we're solely going to just list the possible rational zeros. We're not going to do anything with the solving. So let's look at example 1. So for example 1 here, first thing I would want to do is determine what's my p and what's my q. Again, this is p, this is q. So for my p, it's going to be, I'm going to list all factors for that 16. So for 16, I know 1 goes into 16. I'm going to do them in order from least to greatest. 1 goes into 16, 2 goes into 16, no 3, but 4, yes, 8, and then 16. So those are all of my factors of 16. Again, I'm just mentally saying them to myself as I go through. For 4 is our q, that's our leading coefficient, and our factors of 4. So again, it's not just 4 itself, it's all factors. So it's 1, 2 goes into 4, and then 4. So these are all of our possible factors. All our factors. So now when it comes to all the rational zeros, again, these are the possibles. It's not like they all are necessarily zeros. So these are possible zeros. It's going to be, again, it's always plus or minus. And the best way to do it is just to go straight across. I like to just go 1 over 1. So plus or minus 1 over 1. Now 1 over 1 is 1. So we're just going to write it as 1. We're not going to be worried about all this extra stuff. So plus or minus 1. Then I'll do plus or minus 1/2. I'm going to do everything with the 1 first. And then I'll do plus or minus 1/4. So 1 over 1, 1 over 2, 1 over 4. So now I'm moving on. I'm going to move on to the 2. So for the 2, first plus or minus 2 over 1. Again, 2 over 1. I don't need to write it that way. I can just write it as plus or minus 2. Then I have plus or minus 2 over 2. 2 over 2 is the same as 1, which I already have over here. So I don't need to worry about that one. I'm going to erase it. Again, I don't need to write possible zeros, 1, 1, 1. I don't need to write 1 10 times. So I only need each one once. So the next thing, it'll be plus or minus 2 over 4. Now everyone knows that 2 over 4 reduces to a half. So that's also something I don't need to write here. So keep moving. I'm moving on to the 4. So for the 4, let me switch colors. So now that we're to the 4, I'm starting with 4 over 1. 4 over 1 is the same as just 4, so I'm just going to write it as 4. Then I have 4 over 2, plus or minus 4 over 2. 4 divided by 2 is 2. So that one's already on the list. And then plus or minus 4 over 4. 4 over 4 is the same as 1. So again, I don't need to list that. Move on. My next value is 8. So I have 8 over 1. 8 over 1 is 8. Then I have plus or minus 8 over 2. 8 divided by 2 is 4. We already have that. And then 8 divided by 4 is 2. We already have that. So this is it for the 8. Thought it was off for a second. I forgot about the 16. And then the last one is going to be 16 over 1. 16 over 1 is just going to be plus or minus 16. 16 divided by 2 is 8. 16 divided by 4 is 4. So that's going to be all of my possible rational zeros. All right, let's move on to the next one. For the next one, number 2, again, I want to list all factors of P and all factors of Q. This is my P. This is my Q. So for P, it's 24. And for 24, 1, 2 goes in there. 3 goes in there. 4 goes in there. No 5. Yes, 6. No 7. Yes, 8. 12. 24. And then for Q, we only have 1. So my list of possible zeros, possible rational zeros, is going to be, I'm going to go in order. Plus or minus 1 over 1 is 1. Plus or minus 2 over 1 is 2. Plus or minus 3. Plus or minus 4. Plus or minus 12. Plus or minus 24. So those would be all of my possible zeros for this problem. And then the last one, number 3 here. Well, not the last one, but the next one, number 3. For P, it's going to be 18. And Q is 3. So for 18, again, I want to list all factors of that value. So for 18, we're talking 1, 2 goes in, 3, 6, 9, and 18. For Q, we're talking 1 and 3. All right, so those are all of our factors. So now we have to list all of our possible zeros. So for the possible zeros, again, it's going to be plus or minus. And I start with the 1, and I'm just going to go across. So plus or minus 1 over 1 is 1. And then plus or minus 1/3. 1's done. Moving on to 2. So plus or minus 2 over 1. 2 over 1 is just 2. And then I have plus or minus 2/3. Done with 2. plus or minus 3, and then plus or minus 3 over 3. 3 over 3 is the same as 1, so I don't need that. Plus or minus 6, and then plus or minus 6 divided by 3 is 2, so I don't need to write that one. 9, it's plus or minus 9. Then it's 9 over 3. 9 over 3 is 3, so we're done with that. And then plus or minus 18. 18 divided by 3 is 6, so we don't need that. Those are my possible zeros. All right, so let's move on to example 4. For example 4, I just wanted you to see a situation where the p, in this particular problem, some of you might think that p is 16. Now, technically, it will end up being 16, but right now, there is no p. P has to be a constant. So if you went with 16 at this point, that wouldn't technically be correct. So I just wanted to make sure everyone's clear. Like if you have something like this, you need to make sure you pull out that GCF. In this case, that'll just be x. And then you could focus on, that being your p, etc. But if it's not a constant, it's not doable. You do not want an x with that last term. So keep that in mind when you're looking at the problems. All right, so let's do number 5. So 5 and 6, those are going to be the only two we actually solve, and we're using the rational zero theorem. So if you look at number 5, what's different about 5 from the other problems or the other polynomials that we were solving? If you look at number 5, it has the 4 terms. So if we were trying to solve this polynomial, we should pretty much be trying the grouping method, because again, to solve our polynomials, we pretty much are just going through a process of factoring. So traditionally, again, if there's 4 terms, you should be grouping. So your instinct should have been to group, and then you would take out the GCFs. This one would be x squared. You would end up with x plus 9. For this pair, the GCF is 2. You would end up with 3x minus 8. So when you group, remember in the end, you're looking for these two binomials to be the same. That's how you know you factored it correctly. They're not the same. And there's no way to get them to be the same by just making it a -2 or something like that. So we're stuck. We can't factor. So this is the first one we've come across where we have an x cubed and we can't factor it. And again, we know we can't solve anything if it's not x to the second or x to the first. So we're kind of at a loss at this point. This is when you need to use the rational zeros theorem. Now this theorem allows us to figure out all of the possible rational zeros. So we would have done our p, which is in this case 16. And I don't know if I made it clear before, but you don't have to worry about the sign when it comes to this p and q situation. Because since we're doing plus or minus of all of the terms, anyway, it's irrelevant. You don't have to necessarily worry about the sign when you're listing the factors. Excuse me. So for p, the factors are going to be 1, 2, 4 goes into 16, 8 goes into 16, and then 16. For q, it's just 1. So for q, we only have 1. So for our list of possible, so again, these aren't necessarily zeros, but for our list of possible zeros, we're going to have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Plus or minus 4, plus or minus 8, and plus or minus 16. These are going to be all the possible zeros. Now, when you're doing these type of problems where you do have to use the rational zeros, I want to see that list of possible zeros. If you don't have it, you will lose 2 points. So make sure you write out the entire list, not just the one you used, etc. Now, how does this help us? I'll explain. Now, we're going to cheat a little bit because what I suggest you do is that you go to your graphing calculator. So I'm going to open up mine really quick. So I'm going to go to Desmos here, and I'm going to open up my graphing calculator, and I'm going to graph the function. The reason I'm going to graph the function is because if I graph the function, I'll know kind of what it's going to look like, and I can pretty much figure out what the zeros are now. So I'm going to do x. Which one did I do? I'm sorry, I forgot the problem. X to the third plus 9 x squared plus 6x and minus 16. Okay, so I'm going to zoom in out a little bit. Now, actually I'll zoom out a little bit. So this is what my graph looks like. Now, how does this help me with what I'm doing and trying to solve it? So this, remember that the x-intercepts are the solution. So at this point, if I look at this graph, I already know what my solutions are. That's one solution, that's 2, that's 3. Now, don't get me wrong. You can't use this graph and just go back and say the answers are 1, -2, and -8. That's going to get you absolutely no credit. But if you kind of know what they are, you know which of the rational zeros to try. So I'll explain that in a second. So again, just remember, these are the values that we're going to be using. We're going to use the 1, the -2, or the -8. We don't need them all, but we'll probably use one of them. So let's go back to our graph. So again, if we remember from, I'm sorry, to our sheet here. So if we remember from the graph, the solutions were 1, I think it was -2 and -8. I have the worst memory, but I think those were the solutions. So these are the ones that we should be thinking of trying. So how do we use this? What we're going to do is, because we know that these are the zeros, again, we can't just write it down and say that's our answer, but we know which one of these to try. So basically, if you didn't go to the graph, you would just randomly have to try all of these different numbers. Now, what I mean by try is the following. What we're going to do with these rational zeros is that we're going to use them via synthetic division. So we will take the number here. So one of the solutions was 1. So I'm going to put 1 here. And then I'm going to do synthetic division to see if it's a factor. So when I do the synthetic division, remember, I only take down the coefficient. So this will be 1, 9, 6, and -16. Remember, when you do the synthetic division, the first number just comes straight down, so it's 1. 1 times 1 is 1. We get 10, 10, 16, and then we get 0. As long as your remainder is 0, or you don't have a remainder, that means that this is a root, or it's a factor. It goes into it evenly. Okay, so how do I write this when it comes to the solution, or how does this help me? Remember that since this is my solution, how I'm going to write it in binomial form is going to be x minus 1. Remember, it's always the opposite. And then remember that after I do my synthetic division, I always go down a power. So I started x to the third, so this is going to be x squared plus 10x plus 16. So now I've already got something factored out. I couldn't have done that with the other methods that I was trying to use. So this has helped me factor this. So now I'm going to keep going. So I need to keep going because, again, I mean, I could technically use the quadratic formula and stop, but I can still factor this. Hopefully everyone I'm just going to move it over here, guys, just so I have more space. All right, so hopefully everyone realizes that this is still factorable. 16 has factors of 8 and 2. That gives us 10. So this is going to be x minus 1, and then it's x plus 8, x plus 2. And then I would solve it. X minus 1 equals 0. All right, now it's all factored down. Now I can go ahead and solve it. This would not have been factorable just by using traditional methods. You had to use the rational zero theorem to give you, a head start. So this is a situation where we would have to use this. All right. All right. So let's go to the next example. Example 6. So again, if you look at example 6, there's 5 terms. There's no GCF. A problem like this, you should look at it and be confused right now. There's no way to factor that. And it's x to the 4th, so we know we have to factor it because we can't solve anything that has an x to the 4th in it. We have to break it down to x squareds and x to the 1st powers. So once you get to this point where you can't factor, there's no x squared, there's no x. This is when you have to use the rational zero theorem. So let's look at this problem number 6, and let's figure out what are our possible rational zeros here. So P, Q. So P for this one is 10. So factors of 10 are 1, 2 goes in, 5, and 10. And Q is just 1. Now, some of the previous, I should have said this when I was doing it. Some of the previous problems, we saw some zeros that were like a third, 2/3, like we have here, things like this. Just to be clear, I'm not that it's not possible, but I'm not going to give you anything as a root that's not a whole number. Okay, just so it won't be like crazy difficult with the synthetic division and etc. So I'm going to keep it pretty straightforward and make sure any of the roots are always whole numbers. All right, so anyway, to list the possible solutions here, it's going to be, so possible roots. Again, I want to always see this listed out. It's going to be plus or minus 1 over 1, plus or minus 2 over 1, 5, 10. So right now there are 8 possible things to try. I could try plus 1, minus 1, plus 2, minus 2, etc. I could try all of these different values. So I could just pick one randomly, or I can go to my graph and try something. I'm going to just pick it randomly this time. Let's just see what happens. So I'm going to try 1. Just because 1's easy to try. I'm going to try plus 1. So if I try plus 1, that means I'm using the coefficients. They're 1, negative 6, 9, 6, negative 10. Again, synthetic division is relatively easy, so it's not the end of the world if it doesn't work. Yay, it works. So this gives me 0 as my remainder. So as long as I get 0 as a remainder, that means it worked. So again, let me explain. So what I'm going to put as my binomial will be x minus 1. So since the solution was 1, I would write it in the opposite form here. And then I go down a power, so this was x to the 4th. So that means I'm dealing with x cubed minus 5x squared plus 4x plus 10. So now, again, I could have looked at my graph and got some ideas of what to try, but I'm just going to keep trying things. Now I'm going to try -1. Hey, let's see what happens. So since I'm going to try -1, now let's be clear. I can go back here, but I don't need to go back there. I can just use this, the last value that I got. I don't have to go back and use the big number. I can use this smaller number in here for the synthetic division. So I'm going to use that. I'll have 1, because now I'm taking this coefficient, minus 5, plus 4, plus 10. 1. And that will cancel again. So now I have x minus 1, that's from here. This will come down as x plus 1, because again I put it in as the opposite. And then what's left, this was to the third power, so now I'm starting off with x squared minus 6x plus 10. Now I could try to factor this, but this can't be factored. So now I can solve. My answer is going to be x minus 1 equals 0, x plus 1 equals 0, x squared minus 6x equals 0. My first answer is x equals 1. My second answer is x equals -1. And my third answer, my next answer is I have to use the quadratic formula. So it's going to be a is 1, b is -6, c is 10. Alright, so once I start solving the quadratic here, I end up with 6 plus or minus the negative square root of 4 over 2. Negative square root of 4 is going to be 2i, so it's going to be 6 plus or minus 2i over 2, which can be reduced to 3 plus or minus I. So these are my answers. Alright guys, have a great day. This should be enough to help you do the homework.